I'm Chen Songchun from Department of Construction Management at Tsinghua University, and it is a great honor for me to be here at ISARC 2025. And today I'm representing our research team to share our study, and the title is Semantic-based behavioral decision-making method for construction robots in worker and robot collaboration. So let's begin. So as we all know, the construction industry has faced a lot of challenges such as labor shortage, low productivity, and unsafe working conditions. And the construction robots offer a promising solution to this issue. They can reduce reliance on manual labor, improve the operational efficiency, and what's more, they can enhance worker safety and well-being by minimizing their exposure to dangerous situations. So nowadays there are many different types of construction robots. They are in different shapes and sizes and have its own unique ability. For almost any construction task, whether it is rebar tying, painting, bricklaying, there's likely to be a robot to assist with it. But despite this advancement, the construction robot has not been widely adopted. The major reason is that the construction environment are quite complex and unstructured. And unlike those environments that robots are commonly used. So let's do a simple comparison. First, in the industry environment, the robots are required to perform with multiple tasks, but their working surroundings are quite well structured and with minimal external disturbance. And in the road environment, the autonomous vehicles are required to handle unpredictable conditions to enhance the safety, but their main functions are limited to driving. And in the home environment, their working surroundings are also very complex, but the household tasks are low weighted, so their reliability requirements are much lower. In contrast, in the construction environment, it is very challenging. It involves high scenario variability and a wide range of operation types and much strict safety requirements. So that means for a robot that on a construction site, it has to be robust, to be flexible, and are capable of handling multiple tasks. So that is too difficult for one single robot to do, and that is what worker and the robot collaboration comes in. So we can combine the characteristic of humans and robots to create efficient human-robot teams that in which the human can take more complex and more precious tasks, and the robot can take repetitive and physically demanding jobs. So in this way, we can maximize the value of the robot. And to do this, the role of the robot must evolve. They must shift from simple to, which means it is remotely controlled by the worker, to, we call it a true teammate that can collaborate with workers with a high level of autonomy. So to achieve this shift, it requires the robot to have the behavioral decision-making ability. That means it can determine what to do and when to do it. So our main research purpose is to develop such behavioral decision-making method, and it contains three parts of objectives. The first is to build a scene understanding ability into the robot so that it can understand its collaboration state based on its own observation. And the second is to develop a policy learning method that can allow the robot learn from human experts to decide what action to take under different situations. And the last is to develop a behavioral decision-making method that can allow the robot to make decisions based on its understanding of the scene and the learned policy. So in the next sessions, we'll present the details. The first is the scene understanding part. So in our research, we do not focus on how the robot observes, because different robots may use different sensors like cameras, laser depth camera, or temperature sensors. And what we really want to focus is to fill and organize all these kind of unstructured data into a well-structured and meaningful description that robots can understand. So to do this, we first introduce a semantic-based collaboration state description method. So first, we identified three kinds of entities on the constraint side commonly found. They are agents, movable objects, and static objects. So the agent, they are capable of moving and can interacting with each other. And in most cases, it contains worker and construction robots. And the movable objects, they cannot act on their own and can only be used or moved by the agent. And the examples are tools, materials, and containers. And the last kind of entity is static objects. They are fixed and cannot be moved. And these three kinds of entities interact with others through two primary relationships. We call it a spatial relationship and a kinematic relationship. A spatial relationship means either two entities are at a close distance or they are in touch with each other. And the kinematic relationship means a fixed relationship, one move together with another. So we use these two relationships to describe a state. And in most cases, this method can describe a typical collaboration state, but in construction may limited by the sensing ability of the construction robot, the observation may be incomplete. So if a worker is outside the view of the robot, and then it will not appear on the semantic graph at all. So to address this issue, and we propose a semantic reasoning method based on semantic graph. So it allows the robot to infer the actual state based on its incomplete observation. And so it uses its incomplete observation to match a set of candidate states so that it can estimate the most possible working state. And through this process, the robots can adapt to the dynamic environment. And after the robot preserves the environment, it needs a behavioral policy to decide what action to take under this situation. So nowadays, there are three main kinds of methods. There are programming method, reinforced learning method, and learning from demonstration. The pre-programming method is a rule-based method that relies on humans to set a lot of rules in advance. And the reinforced method is a data-driven method that relies on the reward function to guide the robot to learn behavior policy through trial and error or using a large amount of data. And learning from struct demonstration it combines both rule-based and data-driven. It allows the robot to learn directly from human experts by observing and imitating what they do, especially what action take under different situations, and that is what we adopted. So to do this, we need a platform that allows the human to teach the robot what action to take. And so we built such a platform. It is based on VR and digital twin. So in this system, at least two people are required. One play as the robot controller and one play as the worker. They collaborate to complete a construction task. And in this process, their actions and interactions are recorded to generate a behavioral policy. And the whole demonstration data includes entities, relationships, variables, behavior, robots' behaviors. And after we collected all this data, we align this based on the timestamp. So by doing this, we build a clear connection between the scene state and the robot's behavior, and that we can get a policy. So after that, we need an algorithm that to do this decision making. It contains the global level and the local level. So the global levels, in this global levels, the robot uses its own thing understand result to decide what action to take. It usually has three kinds of outcomes. So the first situation is that there is no matched result in the policy. Then the robot will keep in a default state. In most cases, it means it will keep still or inactive. And if the thing understanding result matches multiple state in the policy, then the robot will also keep in default state to avoid collisions. And if the thing understanding result matches just one single state in policy, then the robot will execute the actions corresponding to this state. And the local behavior decision-making level enhance the robot's ability to adapt to dynamic environment by managing the life cycle of each behavior. So we can set a lot of safety conditions. For example, if a worker gets too close, it can pause or change its movement to avoid collisions. So this enhance more safety collaboration. And to validate our method, we do an experiment. We use the wall panel installation as example. In traditional construction, it needs a worker to hold the panel while using a nail gun to fix it to the wall. And this process is repetitive and physically demanding and may have a risk of hand injury. So we use a construction robot to assist. It has a mobile platform, a robotic arm, and a suction cup. And it has set of skills like move its arms to a designed posture, move its platform to a designed position, and attach or detach its panel. And the installation materials includes the several panels and a nail gun. The whole experiment contains two phases. The first is we call it a demonstration experiment. In this experiment, the participants are required to play the role of the robot controller. They only request to perform specific actions when the subject requests them to do so. And after this phase, their actions are used to generate a policy. And in the collaboration experiment, the participants are required to play the role of the worker, and they collaborate with the robot that are controlled by the learned policy. And we evaluate the whole system based on two metrics, the feasibility of the policy learning and the success rate of the collaboration. This is a snapshot of our experiment. The first is what the workers see in the VR headset, and the second is what the robots see from their cameras. And last is the whole thing, whole view of the whole experiment. A total of 10 participants are involved in this experiment, and their workflow can be concluded as so at first, the worker will grab the panel and hand it over to the robot, and then the robot will move to the work platform. And after that, the worker will use the nail gun to fix it to the wall. After all this is done, the robot detach the panel and move to its original positions. And in this process, the robot performs four main kinds of action. They are grasp, position, release, and the repetition. And the trigger and the transformation semantic graph can be shown in the right figure. So this compose the robot's behavior policy. So at last, 18 out of 20 policies are false feasible. That enables the worker to successfully collaborate with the worker, and the 2 infeasible behavior policy are result from incorrect demonstration. For example, if a worker is asked a robot to do the action or cooperation when he is still hold the panel, so that can cause a conflict. And 16 out of 18 collaboration tasks are successfully complete at the first attempt, and the 2 failed collaboration are result from human error. And after repeated trials, all the participants successfully complete the tasks. So let's do a brief summary. Our main purpose is to develop a behavior decision-making method for constructing robots in on-site worker and robot collaboration, and it contains 3 main components. The first is a semantic-based scene understanding method that allows the robot to observe the collaboration state based to understand its collaboration state based on its own observation. And the second is a behavior policy learned from demonstration that allows the human to teach the robot what action to take on different situations. And the last is a behavior decision-making algorithm that can integrate the policy into actionable decisions. And we validate it in a panel installation task. And this is our findings. First is that the robot comprehension is complex, a dynamic worker and robot process. So that allows the robot to adapt to dynamic environments. And the second is that this method enables behavioral decision making during autonomous collaboration with workers. So this enhances more smoother and more effective collaboration. And at last, this enhance the workers' understanding of robots' behavior. That means it can make workers feel more safe and more confident when collaborate with the worker or we collaborate with robots. And in our future plan, we plan to validate it in real-world settings because all our experiments are in a VR environment, and we plan to integrate the recovery mechanic into the robot's policy, so that allows the robot to can handle different situations like errors or unpredictable situations. And at last, we plan to validate the accuracy and operational efficiency involve multiple workers and robots. And that is all my presentation. Thank you very much.